Welcome on online wireless mobile communication. Today our topic is Hata model. The Hata model is simple model. It is a empirical formulation of the graphical path loss data provided by the Akurma and is valid from 150 megahertz to the 1500 megahertz. Actually, there is some drawback in the Ekorma model, and this drawback uh, uh, is it is does not based on the on a rural area. So the correction is made here for only in a urban area and suburban area, and this is a there is no analytical explanation in a Ekorma model. There are certain causes which cannot be explained. It is the extra polluted. In early days, the models were based on the empirical studies, and Akurma did comprehensive measurement in 1968 and came with this model. It discovered a good model that is for the path loss was a simple power law where the exponent eta is a function of frequency, antenna height, etc. One of the most widely used model for the signal prediction in the urban areas, and it is applicable in the frequency range of 150 MHz to 1920 MHz, can be extrapolated up to 3 GHz, and the distance is taken as 1 kilometer to the 100 kilometer. But now this proposed Hata and extended Hata model, this Hata model is an empirical. Uh, this is an empirical model and of the graphical path loss. Uh, this graphical path loss is data provided by the Akorma and is valid from 150 MHz to 1500 MHz. The Hata presents the urban area propagation loss as a standard formula and the supply correction equation for the application to the other situation. The standard formula for the medium path loss in the urban area is given by the formula. The formula is this is given by the this formula. In this formula, L50 dB is taken the values and in the urban area, and it is the standard formula. There is a L50 in urban minus this values is taken as a this is the formula. It is 69.55 plus 26.16 log FC in megahertz and minus 13.82 log h of Te minus a h of Re and plus 44.9 minus 6.55 log h of Te and of the log D. In this formula, in this formula, this is a L 50 dB, and this L50 is around a is called 50% percentile. It is the known as 50% percentile medium value of the path loss. This is known as 50% percentile of the value of path loss. 50% percentile of the median value of the path loss. So after that there is a one more formula for to uh, attend this question, that is the 26.16 log fc. The important thing is this fc is always taken in the megahertz. So log 50 is in megahertz, and this is a fc is a frequency which is taken having the ranges from 150 megahertz to the 1500 megahertz. Now the next term is minus, this is the minus 13.82 log of h of t. This log h of t is nothing but it is the effective transmitter base station antenna height, which is in meters and ranges from 30 meter to 200 meter. And one more term is here, minus a of HRE. The minus a of HRE is the correction factor for the effective mobile antenna height, which is a function of the size of coverage area. It is the correction factor. And after that there is a another formula in the bracket, 44.9 minus 6.55 log h of t. This is a calculation in h of te. The h of t is the effective transmitter base station antenna height in meter. It is also ranging from the 30 meter to the 200 30 meter to the 200 meter, and as compared to height of receiver, it is ranging from 1 meter to the 10 meter, 1 meter to the 10 meter. So now I repeat this equation, L50 in dV, 69.55, 69 point, this is the 69.55, 26.16 log FCMH minus 13.82 log H of TE minus A H of RE plus 44.9 minus 6.5 log H of T and log distance D. So we have right here, this is log 50 in dV is equal to 69.55 plus 26.16, after that log of fc in megahertz, and it is minus 13 point minus minus 13.82 log of h of te, correction factor a of hre, plus there is a 44.9 minus 6.55 h of t, and it is log of t. The equation which I have here, it is the standard formula, and we are using, this is called the standard formula, and after that there is a some parameter which is used, that is the h of t. This is the h of t is a h of t here h, this is h of t, it is the antenna height, it is the effective antenna height, this is the effective transmitter base station, and it is having the range of height is 30 meter to 200 meter. This one is the h of te, and this is the h of re, this is the mobile station mobile antenna height, effective mobile antenna height, and the range of height is 1 meter to 100 meter, and there is a correction factor a of, correction factor is denoted by a of hre. It is the correction factor for the effective uh, mobile antenna height, which is the function of size of the coverage area, and d is the small d is this separation distance between the transmitter and receiver. And there is a three more formula uh, which is given here. One is this one. Second formula consists of the two formula. This formulas are uh, actually based on the correction factor, mm, and this correction factor are here in our formula. You can see it is the A. This is the our correction formula, and this point is a path correction formula in the medium size or a small size city. This is this correction formula in a medium size or a small size city. So medium size or small size city having calculated this correction factor, 1.1 log fc minus 0.7 multiplied by height of the effective height of the receiver, that is the mobile station, and minus 1.56 log fc minus 0 0.8 in dB. So if we want to calculate this correction factor in a small city, or you can say in a medium city, we have taking the this formula. And if the values are ranging to in a say large city, though there are the two formula for the large city. And first formula, which is uh, uh, carrier frequency fc is less than 300 megahertz, then we have taken this formula. If the carrier frequency is larger than 300 megahertz, then we are taking this third one formula. Normally we are taking the this formula for our calculation. This is the our for the basic calculation. We using this third one equation. This is the basic equation. So here this equation is a 3.2 log 11.75 h of re का whole square minus 4.97 dB when the carrier frequency is more than 300 megahertz. Here one point I made it very clear for the student points of view. Most of the cases we are taking this is the our main formula, and we take the values of this, put it in the into the main equation. The main equation is here, where the correction factor is, where the correction factor, this is the correction factor. We compute the value like this way: a of HRE when the carrier frequency is more than 300 megahertz. Remember one thing, we have taken the values of carrier frequency in only megahertz. Log 11.7.5 h of re का whole square minus 4.97 dB. Now move for the next point. uh, The path loss, which is are given in this formula uh, for the urban area, is given by log 50 dB log 50 dB at log 50 urban minus 2 log h up divided by 28 का whole square minus 4.5. The value of the path loss in urban area is calculated with the help of this formula, and which is given as log 50 percentile values is taken 50% of the urban area minus log h of h of the sorry, it is the this one is the frequency divided by 28. and whole square minus 4.5.4. And if the values is uh, in open rural area where the Akorma model is insufficient to find out in open area, so Hata model is give this solution. The we have taken the values of log 50 at the same log 50 urban minus 4.78 log fc का whole square minus 8.33 log fc minus 40.98. So we have calculate the values in a urban area, and after that we are putting this whole uh, values in the our main equations. So I already told you that that this is the standard formula, right? Now what we do now, what we do we take the values of here a h of re and put it here in the main equation, that is the fc is greater than 300 megahertz. So the values of 300 megahertz at point here is 3.2 log 11.25 h of re ka whole square minus 4.97 dv. This values is taken from this equation. We are using this equation, right? The students are be very careful to take the values of correction factor and put it there and calculate with the help of a Korma graph model. After that, there is some extension in this model, and that extension is come into the form of the personal communication system, that is known as PCS. The personal computer system is known as PCS. So the PCS, personal, P for personal, C for computer, S for system. So PCS Hata model, or you can say extended Hata model, or you can take another name, cost 231. It's also having the euro cost, is another name is euro 91, because the European Cooperative for the Scientific and Technical Research Euro cost has given this cost 231 model. He proposed this model that is known as extended Hata model. So we are taking this into our consideration, and it is the widely used path loss model to determine the path loss with the help of the extension of the uh, mm, previous standard formula. So the Hata model which is working in 2 gigahertz, and the proposed model for the path loss is the cost 231, and we are using this equation that is given here. This is the our equation, right? Near in this equation you have seen a one change is here, that is in the form of cm, the factor which is at the last of the cm is nothing but it is the uh, correction factor when we are taking the medium size city or urban area and the when we taking the metropolitan centers. So the CM values is ranges from 0 dB to 3 dB, and 0 is taken value when the upper city is the medium city, which we are taking the medium city, we are taking the medium city or suburban area, and this values is taken at cm in 0 dB form, and cm is equal to around 3 dB. Our cities is known as metropolitan city. We have taken the metro city where the population are in dense form and users of mobile users are not in a form of the 100 200, in the millions of users are present in this dense area. So the cm factor is ranges in the 3 dB. So this is the restriction in the Hata model in the form of cos 23, and the parameter which are you using in this model are same: h of te, h of re, separation distance d, correction factor hre. This hte is the base station effective antenna height, and it is normally this antenna height in the range of the 30 meter to the 30 meter around 200 meter. This the values of this is 30 meter to the 200 meter, and the values of effective mobile antenna height is around 1 meter to the 10 meter, and d is nothing but it is the separation distance tr and transmitter to receiver, and the values is taken as 1 kilometer to the 20 kilometer. So the values which are taken as d is 1 kilometer to the 20 kilometer, and the values of t is 30 meter to the 200 meter. The values of re is taken as 1 1 meter to the 10 meter, 10 meter. So this is all about in Hata model, and I am giving the one advice to the students. Please uh, solve this numerical which I have given here, and I read out the equation that is the I have written here. Employing the Ekurma model, compute the medium loss at a distance of 10 km when the carrier frequency fc is 2.1 GHz. Assume h of t is 40 meter, h of re 2 meter, and for a large city. If EIRP is given by 1 kilowatt at the carrier frequency, find the received power for the same scenario. Also use the same condition to apply over a Hata model and comment on the same. So we are going to solve this problem. How do we solve? How do we solve How do we solve? By using a Kumurma model path loss equation. Remember, in previous L50 module I have given LF. L50 is the 50% percentile above the received signal and 50% of the percentile below the signal. That is the median path loss. And after that there is a LF. LF is the free space propagation loss. There is a one more term, that is the AMU. AMU is the medium attenuation relative to the free space. This is the medium. This is calculated from the Hata graph, and h of Te minus G h of Re minus G area. The gain of transmitter antenna, the gain of receiver antenna is with respect to base station and the mobile station, and the effective area, that is the correction gain due to the type of the environment. And using this equation we can solve the problem. The carrier frequency which is given, that fc is 2.1 gigahertz. So I am already said you take the values this gigahertz into megahertz. To convert this into a megahertz, we can write 2.1 into 10 to the power 9 this hertz. So it is, now you can say 2.1. How much the values of this in the megahertz, you can say into 10 to the power 3 megahertz. So using this formula and put it into your equations, and we can solve the lambda. And lambda is nothing but this is the speed of light to the center frequency which is passes in the free space, and put all the values. The free space light is 3 into 10 to the power 8, and this one is nothing but it is the this is given by 4.1 and into 10 to the power 9, and these values we are calculated coming around 0.143 meter. And the value of LF, we know the value of LF is computed with this equation, log 10 log d square 4 pi square divided by lambda square. And after the putting the values, d square is the separation distance, that is given 10 kilometer, and 10 kilometer is converted into the meter. So we can write it is the square, and it 4 into pi की value is taken 3.4, and it is square divided by lambda square. Lambda is calculated from, put it these values in equation in there, and we can take a square of this. So the values which are coming is around this values is coming 118 dB. 180 dB. Approximate values is 180 dB. So LF is 100, free path loss is 118 dB. Now go for the to calculate h of TE at 40 meter and h of RE at 2 meter according your question, which is ask this calculate. Then we are taking the values of h of t is equal to 20 log of h TE divided by 200, and the value of this 20 log, put the values of h of t 40 divided by 200, so it comes around minus 40 dV, minus 40 dV. Or for HRE, this is the value of 2 meter, it is less than 3 meter. So the values which I have taken here to calculate, compute this H of RE at the base of log 10 HRE divided by 3, and put all the values in equation. The formula we write getting minus 7.6 dV. 7.6 dV. So uh, two more constant which we want to calculate. One is the AMU at 2.1 gigahertz. Distance is 10 kilometer. It is this values is computed from the graph, and the correction factor G area is also for the large city. This is, remember, question is asking for the large city area, and we are know that for the large city area correction factor, when the values are 3 meters, is less than a Hata model. We are taking the values around that is approximately 0 decibel, because the area is very large city, and the propagation delay is there is a line of sight there, so there is no propagation delay. So the values of G area large city is 0, and compute this value of AMU from the graph. So we are seeing the graph AMU. Look at this. From this from this from this there is a x-axis. This is the frequency. This is the Hata model. In a question, we are this one is the graph which is produced by the Akurma, and this is in this axis we have taken the frequency in megahertz, and it is ranges from the 100 megahertz to the 3000 hertz, 100 megahertz to 3000 hertz in a x-axis, and in y-axis there are the two axes. First axis, which is a mark here by the double arrow, it is called separation distance D in kilometer, and the another axis which is I having the single arrow, this y-axis is the attenuation HAMU, attenuation factor, and which is calculated on this scale. So the question is asking at 2.1 gigahertz, this in this you have looked, this is the 200 hertz, and around 1, this is the 2.1, and the this are the distance 10 kilometer. So draw the perpendicular on it and take it the over here. It is coming around from the values is this values is calculated h of 200 meter and h of r is 3 meter. So value of AMU which is calculated is 34 dV. I am saying the students you are taking this in a proper scale and put it here, then you are getting the exact 34 dV. And here the values which are we are taken in the question is asking the HRE is 2 meter. So the values which are taken for the formula to calculate the GH of RE is 10 log H of RE divided by 3. So that's why we are taking the computation to compute these values uh, for there only. So resume to back our main problem and to solve to solve to solve the next step. L50 we already know it's LF plus AMU minus GH of TE minus GHRE minus G area. So put all the values. LF is calculated 118, AMU calculated 34, and this GHTE is minus 14 dV, and HRE is also in minus 1.78, and this minus G area is 0. So the L50 is approximate 167 dV. This is the path loss, or it is only due to a Kumura model. This is only for the Acura model. This is done here, and I show what we did and what we show. Look at using the Ekorma path loss model that L50 equal to LF AMU minus GH of T G H of RE or G area. This L50 is 50% percentile of median values above the received power and below the 50% of percentile below the received power. LF is the free space propagation loss. AMU is a medium attenuation factor. GHTE is nothing but it is the base station antenna height gain factor. It is the again the gain factor, but it is the mobile station antenna height gain factor. This is the G area which is gained due to type of the environment effect, and the carrier frequency is given 2.1 gigahertz. Now we shown it is converted into the megahertz. Put it these values to calculate compute the value which is coming 0.1.43. Now what we do now we have calculate these values and put it in this free space path loss model, that is the 10 log L lambda square divided by 4 pi square into d square. Remember there is a one more terms, if you remember, upon 4 pi square into d square there is a one more term L. Here what we considered the GR and GT are unity gain. So we put this unity gain is equal to, here we taking the L is 1. So then after that we have taking this formula and put it here. to compute the free space path loss. And again, we are know that the values of this put it here to compute this gain of this antenna height of receiver and transmitter, uh, and proceed here to in for the main equation, and the values which are calculated here I am shown there. Actually, if you are doing these the numerical, then you have realized you are well familiar with this formulas. Otherwise you have having stuck to solve this problem. So please see this how to solve, and if any problem you can ask. And now move for the Korma model to the Hata model. The formula is L50 is equal to 69.55 plus 26.16 log FC minus AHRE plus 44.9 minus 6.55 log H of TE log D, and minus 13.82 log H of TE. So the questions here we have taken is very uh, important, and to solve this problem, so we have writing once again this formula. This is the L50 is 69.55 plus 26.16 log FC minus 13.82 log H of TE, and correction factor ARE is uh, third one equation, and we'll write this third order equation is put it 3.2 log 11.75 HRE का whole square minus 4.97. So proceed again and put it all the calculation here for taking the values of FC converted into the megahertz, and it is around this is a 2100 megahertz, and log FC can take the values of at the log base. Log 200 is coming around 3.3322, and after that it is multiplied by the 26.16, it is coming 86.9. Okay, okay, after that calculate this 444.9 minus 6.5 log H of TE. So H of RE. So this value is coming 10.49 around something it is coming, and so you are going to compute ARE. ARE is coming around the values of ARE is 20.4. So this is HARE, and you are calculating after this values. All values are here is, now I am going to write what we calculate. AHRE, that is 3.2 log 11.7 HRE का whole square minus 4.97. HRE is 2 meter, put it here in here 2, so the values are coming is 1.04 dB, right? And the values of this 26.16 log FC, put it 26.16 log 200. Okay, and it is coming around 11.4. This values is coming uh, something like, calculate 26.16 log FC, 26.16 log 2000, that is the 75.94. And for 13.82 log h of t is te is given 40. So in place of h of t you put the 40 meter. So this values is coming uh, around minus, this values is 20.41. And one more term is there, 44.9.6.5 log h of te, and this is multiplied by log d. Here d is given that it is the 50 kilometer, so you have converted better it into the meter, and after the putting the values in the meter, this values is coming around 149 dB. Okay, so do now calculate L 50, which is 60.955, 70.594 minus 20.41 minus 1.05 plus 140.90. So the values is coming around 164.93, approximate 265 dB. When you are calculating the path loss in a Hata model, it's coming 265 dB, because in this there is a line of sight that is 110.5 dB in calculated in the previous. I show you have calculated here this LF, you already calculated. This values is nothing but it is coming around the something like uh, free space is 110 dB. This values is 110 dB free space. This is a korma. There is a direct line of sight, but the obstacle and the rain is the main phenomena which which are having the some correction some correction factor, and this correction factor is increase the receiving signal strength, because the some of the signal is not reaching in a proper time, they having the delay time, so the power dissipation is increased, so the power losses are increased, so the path loss is also increased. Due to that, we have getting the values uh, are in Hata model is around the 265 265 dB as compare to direct line of sight. I hope the students are doing this in numerical, and if they are having any problem to ask me. Thank you very much. Today is only this much. Thank you.